All right, welcome back to lecture 9. This should be the last lecture on thermodynamics. So again, quickly, last time we talked about reversible versus irreversible processes, the definition of those two, and the first statement of the second law of thermodynamics, which says heat never flows from a colder object to a hot object simultaneously or spontaneously. So which means naturally. Okay, so naturally that's not the case. And we look at the heat engines. So for heat engines, there are three components: hot reservoir, cold reservoir, and the engine that does work. Okay, so those are the three components. Mathematical relationship is T or QDH equal to QC plus W. So QH being the heat absorbed by the engine from the hot reservoir, QC being the heat discarded to the environment from the engine, and then W is the work by the engine. Efficiency then is defined as the work done by the engine divided by the heat takes in, so W over H, and it could be having two other different forms, QH minus QC over QH or 1 minus QC over QH, okay? Now the heat pumps and refrigerators, so this is the other way around, that heat actually flows from the cold reservoir to hot reservoir. But in this case, you need to do additional work, okay? So the work and then is being done by the heat pumps or refrigerators. So it's the reverse way of how the energy flows compared to the heat engine. Okay, so for a refrigerator or heat pump, so it goes in like this QC from cold reservoir through the refrigerator with the additional work W and dumped QH to the hot reservoir. So again, QH equal to QC plus W all still stands here. In this case, for the heat engine or for the pumps, AC, refrigerators. So when we talk about the QH, QC, and W quantity, so these are all positive numbers, or think about take absolute values of those numbers, okay? For refrigerator, coefficient of performance can be calculated. So basically, it's the efficiency of the refrigerator. So when you buy a refrigerator, look at that parameter. So QC over W is the coefficient of performance, which means how much heat you can remove from the food inside the refrigerator divided by how much mechanical work is needed. In this case, the electricity consumed, the electrical work by the refrigerator, okay? Or QC over QH minus QC. The air conditioning works the same way as the refrigerator. Now think about the whole house as the refrigerator. Okay, so in that sense, that you take the heat away from the inside air of the house with the AC that takes in the electrical work and dump the heat to the outside air in that case. Heat pump also the same way, but in this case, the heat pump is the opposite of the AC in terms of the inside and outside air, or the cold and hot reservoir. Okay, so in this case, the cold reservoir will be the outside air, the heat being removed from the outside air with the electrical work by the pump, so that pumps the heat into the hot reservoir inside air inside the house. Okay, but it's pretty much a bigger refrigerator. Or the other way of how the AC works. Okay, the reverse way. So for heat pump, you're also looking for the coefficient of performance, which is how much heat it can supply to the inside air, QH over W. Or you can do QH over QH minus QC in that sense. So you're using QH this time. Two more statements of the second law we explore. So Kelvin's statement and Clausius statement. So basically, you cannot have a perfect engine or a perfect refrigerator in short sentences then. We also look at a Carnot cycle, which means we are assuming everything happens so slowly, so this engine can be treated as ideal engine. Okay, so then the Carnot engine is the ideal engine. It will have the highest efficiency possible for the engine. So it turns out it's this efficiency, the highest efficiency determined by the two temperatures of the cold reservoir and the hot reservoir. So E equal to 1 minus QC over QH or equal to 1 minus TC over TH. Okay, so if you know the two temperatures the temperature of the hot reservoir and cold reservoir, you can calculate what will be the maximum ideal efficiency of an engine. For heat pump AC, so for the refrigerator, which is similar as AC. So for refrigerator, you do QC over W. And in that case, QC over QH minus QC. The ratio of QC and QH are proportional to the temperatures. So again, that can be calculated as the temperatures of the two reservoirs. Okay, so TC over TH minus TC. Now for heat pump, that will be TH over TH minus TC. Okay, all right. So we didn't talk about the power plant. So power plant can be also treated as an engine. So where typically you have heat takes in from different sources. So conventionally it's the burning of fuel. So then that heat up the water here that makes the water boiling. So it's called a boiler. So steam then it's generated that goes to the turbine here, so makes the mechanical work in that sense. So which generate electricity, okay, for the usage. So and then the returning of the steam will be condensation condensed through this reservoir over here, which is the hot cold reservoir. So hot reservoir here, cold reservoir, and this is the engine. So the maximum efficiency for this thermal power plant, so that will be TH minus TC over TH, okay? All right, nuclear power plants works the similar way as the thermal power plant. So the heat generated from the nuclear reactors used to heat the steam, and steam goes to the turbine and then the coolant, and goes backward. Okay, so with excess heat now dumps to the cooling towers. Okay, so the same way. And if you see those cooling towers, that is the for the nuclear power plants. All right, so today we are going to focus on entropy of a thermal process. So in general, irreversible processes causes us to lose some energy in some certain form. So then the heat. So then not all the heat that takes in can be converted into work eventually. Okay. So this is based on the concept of entropy is based on the Carnot cycles. So where the QC over QH is proportional to temperature, TC over TH. Okay. So there's hot reservoir, there's cold reservoir. So we can move things around, parameters around. So we have the parameters associated with the cold reservoir on one side, and then the parameters with the hot reservoir on the other side. So then we get this QC over TC equal to QH over TH. All right. So similarly, that as we have been doing so far. So when you have like quantities with associated with one state, then we can call that as a new quantity. So in this case, we can call it as entropy of that state, okay, or entropy change in that sense, in that case. So then Q over T, the heat change over the temperature is the entropy change, okay? So in this case, delta S, so refers to the initial and final status. Okay, now in differentiation form, if you do this slowly, then differentiation form will be derivative of S equal to dq over d over t. Okay. All right. So let's take a look on a couple of examples on entropy first. So it says a heat engine operates between a high temperature reservoir at 610 Kelvin and a low temperature reservoir at 320 Kelvin. In one cycle, the engine absorbs 6,400 joules of heat from the high temperature reservoir and does 2,200 joules of work. What's the net change in entropy as a result of this cycle? Okay, so there are two reservoirs involved. So the net change in entropy should be the entropy change of the hot reservoir plus the cold reservoir. Okay, so let's take a look on this one. So as the definition shows, the entropy change delta S is equal to Q over T. So you'll have the total net entropy change net equal to entropy change of the hot reservoir plus entropy change of the cold reservoir, right? And that should be equal to Q of H over T of H plus Q of C over T of C. Okay. So when you calculate entropy change, if your temperature is constant, for these two scenarios, hot reservoir and cold reservoir, that's the case because temperatures are constant. So then you can use this, okay? If your temperature is changing for the process, then you'll actually use the derivative of entropy equal to derivative of Q over T. And then from there, you integrate, okay, to get the delta S, okay, should be equal to the integration of derivative of Q over T. Okay, and oftentimes this derivative of q should be a function of t. So then you it can be written as the like derivatives of t in that sense. Okay, so we'll take a look at another example just in a little bit. But for this one, the temperatures of two reservoirs are constant. Okay, so we can just plug in the numbers there. Oh, actually, I think we are given, so let's take a look on the numbers given. So for the hot reservoir, 64,000 joules, okay? For the Q of C, you can calculate easily QH minus W. So it gives you W, so 6400 minus 2200 joules. So end up with 3200 joules, okay? Now, when we actually plug in the numbers here, so in this case, when you're calculating the entropies, okay, so pay attention to the signs here. So for the hot reservoir, it actually loses heat. So this guy should be then negative, okay? So this guy will be negative. The cold reservoir, it actually receives heat, so it's positive, okay? So cold Q of C, that's positive, okay? So pay attention to this guy because Q for the hot reservoir is minus, it loses heat. All right, so minus 6400 joules then divided by temperature 610 Kelvin plus 40, this is actually it's 4200. For the cold reservoir will be 4200 joules over the temperature of it is 320 Kelvin. Okay, so this gives you 2.66 joules per Kelvin. Okay, and note that this is actually greater than 0. Okay, so we'll use this conclusion later on to examine like what should be the total change of the entropy for the system. Okay, so that's this one. Now back to the slides, and then we'll be looking at a second example. Okay, so in this case it says compute the change in entropy of 1.00 kilogram water with its temperature increase from 15.0 degrees Celsius to 100 degrees Celsius. Take the specific heat capacity of water to be 4186. Okay, so C of water is given as 4186 joules kilogram times Kelvin. Temperature initial is 15.0 degrees. Temperature final is 100 degrees Celsius. Okay, the mass of the water is given as 1 kilogram. All right. So let's take a look now. So in this case, your temperature is changing. So this is changing temperature, okay, from initial to final. And they are given in Celsius, okay? So you might want to convert them into the Kelvin. And the same thing for the previous problem. If the temperature are given in Celsius, you want to convert them into Kelvins to plug in the equations, okay? The equation there. So, but let's take a look on this one because your temperature is changing. So we'll be using this expression for the entropy change instead of this guy, okay? So changing entropy then equal to derivative of Q over T. Now for the Q, heat change according to the definition is MC delta T, okay? So then dq, if you do dq, mass is constant, c is constant, so then it will be dt. Okay, so dq will be equal to mc delta derivative of t. So then this becomes mc dt over t from initial to final. Okay, So this is how you would calculate your change in entropy. MC is constant, so it'll be just MC integration of dt over t, and from t initial to t final, okay? So integration of dt over t, t being the variable, so then this gives you natural logarithm, right? So the result will be MC natural logarithm of t initial and t final, okay? So plug in that guy minus plug in that one. So MC of ln of t final minus ln of t initial. And ln natural logarithm of a minus natural logarithm of b will be natural logarithm of a over b, right? So then your change of entropy is MC natural logarithm of tf over ti, okay? So that's your expression. You can plug in the numbers, 4186 joules over kilogram Kelvin times, oh, this is C, sorry. So the M is 1. So I'm doing M here, kg. MC line of T final. T final should be 100, right? Plus 273.15. And T initial is 15 plus 273.15. Okay. So in this case, you can see you're not doing the difference of the two temperatures. So you need to convert them into kelvins. All right, so that gives you delta S equals 1082 joules over Kelvin. Okay, so again, make a note here. This guy is again greater than 0. All right, now let's go back to the slide. Okay, so let's take a look entropy of an ideal gas. Okay, so entropy change of an ideal gas. So for ideal gas, you have PV equal to nRT or capital N small kt. And the ideal gas should also obey the first law of thermodynamics, which says derivative of internal energy equal to derivative of Q minus dW. And in general, you can apply this equation to calculate your change of entropy, so integration of both sides. So derivative of Q over T. For the change of entropy, if you do integration of that guy, okay, so let's take a look on why. So the conclusion here, let me just throw this out first. So the conclusion is for ideal gas, you can use this one for calculating the change in entropy, okay? But it's based on first law, ideal gas law, and then the how you calculate the entropy. All right, so let's derive the equation. Okay. Piece of paper here. So starting with dq, or actually derivative internal energy equals to dq minus dw, right? And then to calculate, so ds is equal to dq over t. Okay, so you need to use this dq. So from here, you can see that dq is equal to then d internal energy plus dw. All right, and then for dw, if you remember, is p dv. Okay, so then this is q internal energy plus p dv. So this would be your dq. So take that into there. So then you got derivative internal energy over t plus p dv over t. All right. Now applying ideal gas law, PV equal to nRT. So P is equal to nRT over V. So this guy, this P then is the nRT over V. Okay. And for ideal gas, we know that the internal energy is only equal to CV times delta T times T. Sorry, not delta T. Okay. So in that case, then derivative of internal energy is equal to CV dt. Okay. So then the first term here now becomes the CV dt over T. The second term will be nRT dV over T. Oh, and over V, not T. Sorry. Yeah, and then over T. Okay, so nRT over V being P, and then there's T from here originally. You can see that this guy, T and T cancel. Okay, so that's your D of S. All right. So if you now integrate both sides of the equation, right? So ds then equals integration of cv dt over t plus nr over v dv. Okay, so that's dt over t, dv over v. So then this will be giving you cv natural logarithm of t plus nr natural logarithm of v. Okay. So, and then if you are doing from T1 to T2 here for the first term, so integration both sides, right? Both terms. So V1 through V2. Okay, so then this is S1 over S2. So then at the end, delta S should be equal to CV, our natural logarithm of T2 over T1. So final over initial, and then plus NR of ln of V2 over V1. Final plus over initial. Okay. And that's what the slide says. Okay. All right. So then whenever you get ideal gas, you can use this equation, okay, for the calculating the entropy change. All right. So we can examine like the for example the isothermal expansion process where T is being constant. So if T is constant, T1 equal to T2. So then this guy equal to that guy. So then T2 over T1 will be 1. So natural logarithm of 1 will be 0. Okay. So changing entropy then just reduce to this term over here. Okay. So this is for the isothermal process. And because you have isothermal process, the internal energy change will be equal to 0, which means Q minus W equal to 0. Now, we have calculate for isothermal process. If you you can check your previous note, but for work done is equal to nRT ln of V2 over V1. So then Q will be equal to this as well. Okay, so the surrounding then in this case, if the gas system expanded isothermally, this so the surrounding loses Q of heat. All right, because the gas expands, so that means it actually absorbs heat in, right? So the surrounding loses heat. But for the entropy change for the gas system is this guy. For the surrounding, it loses heat, so minus Q over T. So this is the gases, and then this is the for the surroundings. So the two add up to be 0. Okay, so this is for isothermal expansion, one of the quasi static processes that we mentioned earlier. All right. So then it turns out this to be equal to 0. The total change for the gas and the surrounding add up to be 0. Okay. So we haven't so far seen any scenario for the total change of entropy, the gas plus the surrounding to be greater than or less than 0 or negative. or for the between the two objects, the hot reservoir and cold reservoir. Okay. So for a reverses process, the entropy change will be 0. Now for the previous two examples, right? So you heat up an object, right? Or you actually have the heat transfer from hot object to cold object, right? So for that process, the entropy change will be greater than 0. Okay. Now for these, so this conclusion based on what we have seen or in general is that if there's no change to the surrounding, so then, or actually, let's go back here. Okay. So the conclusion is for any process in the universe, okay, so the entropy change is not going to be negative. Okay, it's either going to be, so you have to account for both the system of your interest plus the surrounding. Okay, you can just pick one and then forgetting the other. Okay, so they add up to be either 0 for quasi-static process or for irreversible process. Okay, so for a reversible process, it's going to be 0. For irreversible process, it's going to be much greater than 0. All right. Now, the example we mentioned earlier at the beginning of the chapter, so for irreversible process, so you make a hole of this compartment here, the wall of these two compartments, so then gas molecules will diffuse into the other compartment. So this is an irreversible process. So for the entropy change, okay, because you are doing this slowly, so temperature is equal to 0, or temperature is the same, initial and final. So that then the same thing as initially, you have the change, or let's go one slide. So T equal to 0. So the change in entropy will be the same. Okay, so in this case, NR line V2 over V1. Okay, so initial volume and final volume being greater as twice of initial. So natural logarithm argument becomes natural logarithm of 2. Okay. So this is for the gas system. Now the surrounding, this is well isolated. So the surrounding outside of the box, there's no change. Okay. So the surrounding will be 0 for the entropy. So the total change of the system plus the surrounding, we typically call it universe. Okay. To be just this guy greater than 0. So this is for irreversible process. So irreversible process is always going to be entropy change of the universe is always going to be greater than 0. All right. So let's take a look on the example here. So this one says 2 moles of ideal gas at 400 Kelvin expand quasi-statically and isothermally from an initial volume of 40.0 liter to a final volume of 80.0 liter. What's the entropy change of the gas? What's the entropy change of the universe for this system? All right. So you think about okay. So it says N is equal to 2 moles. So let's list the knowns first. Initial temperature T1 is 400, and that's the same as T2. So just say T1 and T2, so both being T. Final volume or initial volume 40, final volume 80. Okay, it says quasi-statically. Okay, so quasi-static, that means implies actually it's going to be a reversible process. Okay, let's take a look on this. So what's the entropy change on the gas? So you can imagine you have like a piston over here, right, which can be removable or can move. So initially this is 1/2, and then the final will be somewhere here. Okay, so initial and final. So V1, V2, in a sense. Okay. So for the gas system, because it's the ideal gas, so you can use this equation. Okay. So for A, delta S is equal to CV ln of T2 over T1 plus NR ln of V2 over V1. Okay. So T1 and T2 being the same, so T1, T2 over T1 is 1. So this thing is equal to 0. So the first term is equal to 0. So then just the second term. V2 is 80, V1 is 40, so this is 2. So this is then just NR ln of 2. Okay. So N is 2 moles, R is 8.31 joules over mole, and okay. And ln of 2. Okay, so this is what you have. So this is what gas. Okay, let's just denote it as gas. So delta S of gas is equal to these 2 times 8.31 times ln of 2. So that gives you 11.52 joules over Kelvin. Okay, so there's Kelvin there as well. Okay, so this is part A. Part B, it says what's the entropy change of the universe for this whole process. Okay, so as you can see, in this case, this guy expanded, right? So it actually does work to the surrounding. At the same time, it should take in heat, okay, for that purpose. So that means the environment actually loses heat. Okay, so let's calculate how much heat the environment loses. Okay, so for change of internal energy is equal to Q minus W. So that tells you, because T is the same and this guy is only determined by T. So that would be like 0. Okay, so this one will be 0. So then Q equal to W. And we can calculate for W. So for ideal gas isothermal expansion, right? So I think we all are very familiar with this now. nRT line of final over initial. Okay. So this will be or let's just leave it there. Because it's going to be nR times T, right? All right. So for the environment, for the surrounding, let's call it environment. Because it loses heat, right? It supplies heat to the gas system. So then it should be minus of this number. So minus of nRT, ln of V2 over V1, okay? And divided by T, okay? All right, so you can see this T and this T actually cancels. So this is going to minus of nRT, ln of V2 over V1, okay? And looking at this for the gas here is actually equal to that guy, right? Now, environment is negative on that. So you can compare this one and this one. So you'll figure that for the total universe, the entropy change should be equal to 0, okay? Because this is a quasi-static thermal process. So it's a reversible process. For the system itself plus the surrounding should be equal to 0. All right, go back to the slide. Okay, so I think we have talked about the entropy change definition, delta S equal to Q over T, right? Now, could there be ever a chance that T equal to go to 0? Now the answer is actually no, we haven't. So that's the absolute value, okay, of any object in the or any system in the universe. But we haven't found anything in the universe or in the or any system in the universe will have temperature equal to absolute 0. Okay, so so it turns out that absolute 0 is actually not reachable, at least, okay, and for right now. So this statement is considered as the third law of thermodynamics. Okay, so absolute value is unreachable. All right, so we have concluded this chapter, and then that will conclude also the how much we need to cover for thermodynamics in this class. Okay, so I will see you in the next lecture then. Bye.